Okay, so in the previous video, we learned about how to do series circuit calculations. When you have a series circuit, the lights, you would have like lights in a row or something in a row connected to a battery, let's say. So in that scenario, that's a series circuit. But now we're focusing on parallel circuits. And in a parallel circuit, the lights are connected in parallel, which means like if you have a light here and a light here, you have a wire hanging off of each of these. You connect the ends together, and then those ends go back to the battery, like so. Okay, so this is a parallel circuit, and electrical engineers draw that parallel circuit like this. Okay, so I've drawn a parallel circuit, and we're going to learn how to do calculations on it to find out how much current and voltage is going through the different resistors and what the total current and voltage is, just like we did in the series circuit. So in a series circuit, we found that there was current stays the same. Remember, current stays the same because there's only one path for the current to flow. But in a parallel circuit, you can see that if the electrons are flowing down like this, the electrons have two paths. They can go this way or they can go this way. So when you add a resistor on in a parallel circuit, it's giving the current more places to go, which means it's actually lowering the overall resistance. But in a parallel circuit, you can see that if I were to take a multimeter and I measured the voltage across, the positive, negative, it would measure the voltage of the battery. So if I did that here, it would measure 12 volts. If instead of doing it right there, I could connect it here, and it would still measure 12 volts because it's just wire. There's not very much resistance in a wire, and so it would still measure 12 volts. If I measured it here, it would be 12 volts. And if I measured it here, it would be 12 volts, as well as here. So you can see that in a parallel circuit, the voltage stays the same. And what does that mean? That means that if we looked here, we could say, oh, the voltage across resistor 1 is 12 volts, and the voltage across resistor 2 is 12 volts. Okay, the other thing about parallel circuits that are different than series circuits is that in series circuit, every time you add a resistor or a light or whatnot, you add resistance to the circuit, and you just add up all the resistances to find the total resistance. But now in a parallel circuit, we're using a new equation, and so I'm going to write that here. As we said, that every time you add a resistor, it lessens the overall resistance of the circuit because it allows there to be more paths for the current to flow. So the equation to find the resistance of a of a parallel circuit is 1 over RT. RT is like the total resistance. The T stands for total, over 1 over R1 plus 1 over R2. And if there was more resistors, we could keep going. Okay, so that's the equation for total resistance. So now what we're going to do is we're going to solve this problem to find all the different values that we can find. So I like to start with RT. So here, if we're trying to solve for RT, we can say, okay, 1 over RT is equal to 1 over R1 plus 1 over R2. And now we can just plug in the values that we have. We can see from up here that R1 is 4 ohms and R2 is 4 ohms. So when we plug that into the equation, this would be 1 over 4 plus 1 over 4. Now, it has a common denominator, so that would be 1 plus 1 over 4, which is 2 over 4. And we can reduce that because 2 over 4, both of those are divisible by 2. So we can make this 1 over 2. Okay? So we have 1 over RT is equal to 1 over 2. But you can see that I'm in the middle of a video, making that video lesson. So you can see that the total resistance is in the denominator, not in the numerator. So how do we get it in the numerator? We're going to take the reciprocal of this. The inverse. We're going to flip that. But whatever we do on the left side of the equation, we have to do the same thing on the right side of the equation. So if we flip both sides, we get RT over 1 is equal to 2 over 1. Or you can just say RT is equal to 2, and the units are ohms. So that's a much more difficult process than in a series circuit, but we finally got to our answer. So the total resistance here is 2 ohms. So we can put that value here. Okay, I'm going to erase this, and now we're going to try to find the total current of this system. So here, now I like to draw things so that you can kind of see, because it gets confusing to try to figure out where to do what. But now if I put all my total values over here, I can say, okay, well these are all my total values. This is my total voltage. This is my total resistance. And now I need to find my total current. So I can use my equation, V equals IR, here for the whole system. VT is equal to IT, RT. And now I just plug in the values. What do I have for V2? It's 12 volts. IT is unknown, it's our variable, and RT is 2. So we have 12 is equal to IT times 2. So now, if I say 12 is equal to IT times 2, to get IT by itself, you have to divide both sides by 2, and you end up with IT, or the total current, is equal to 6 amps, because it's 12 divided by 2. Let me do that, move back. 12 divided by 2, which is 6 amps. Okay, so here we have our total current, our total resistance, and we were given the total voltage. Okay, so now we want to find the current through each of these legs. This is a parallel circuit, and the current does not stay the same in a parallel circuit. So we need to solve for these. So now we're looking at locally here. So now we can apply that equation there. So again, now we say V1 is equal to I1, R1. And we plug it in. So V1 we have 12, I1 we don't have, and R is 4. So now you could say 12 is equal to I1 times 4. Divide both sides by 4. Those cancel. And you have I1 is equal to 12 over 4, which is 3 amps. So now we have our I1, our V1, and our R1. And now, last but not least, we're going to do that over here, locally over here. So here we have V2 is equal to I2, R2. 12 is equal to I2 times 4. So 12. You divide both sides by 4. So I2 is going to be 12 over 4. So I2 is going to equal 3 amps, just like over here. Okay? So now we have solved for everything. Okay? All right, I'm going to erase this, and then I'm going to give you another example to try to do. So let's see. Try to do this really quick. Okay, so now we have R1 is equal to, let's say, 8 ohms, and R2 is equal to 8 ohms, and let's say this is 32 volts. Okay, and you're going to solve for RT, you're going to solve for IT, you're going to solve for V1, and I1, and V2, and I2. Those are the things you're solving for. So pause the video and try to solve those, and then I'm going to solve them for you, with you. Okay, so let's start with RT. I'm going to move kind of quick, but feel free to slow this down. So 1 over RT is equal to 1 over 8 plus 1 over 8, which is equal to, because that's our R1 and our R2, right? This is R1 and this is R2. So that's going to be 2 over 8, which is 1 over 4. So 1 over RT is equal to 1 over 4. We take the inverse of both sides, and we end up with RT over 1 is equal to 4 over 1, or RT is equal to 4 ohms. So now we have VT is 32, RT is going to be 4 ohms, and now IT is what? We need to solve for that. So I'm going to erase this down here. So VT is equal to IT, RT, and we plug in these numbers. VT we have 32, IT is our variable, and RT is 4. So IT is going to be 32 divided by 4, which is 8 amps. So we have all our total values. Our total current is 8, our total resistance is 4, and our total voltage is 32. Now we know that the voltage stays the same in a parallel circuit. So V1 is going to be 32 volts, and V2 is going to be 32 volts. And now we just locally apply that same equation. V1 is equal to I1 R1. So we have 32 is equal to I1 times 8. So I1 is going to be 32 divided by 8, which is 4 amps. And this is going to be the same over here. V2 is equal to I2 R2. V2 is 32. I2 is our variable, and R2 is 8. So I2 is going to be 32 over 8, which is 4 amps. So now we have the voltage everywhere, the current everywhere. And notice this. You have 4 amps coming up through this leg, right? And you have 4 amps coming up through this leg. They merge when they get over here. And you have 4 amps and 4 amps. And so altogether, you have 8 amps. And you can see that that is exactly what our total current is over here. Okay? Thank you for watching.